Hi everyone, today we're going to be looking at composite functions. So let's have a bit of a look and see what we're doing here. So when we have composite functions, it's a function inside a function. So what we're looking at here is that this function g of x is inside of our f of x function. So for example, if I had the function sine of x squared, this is a composite function because the x squared is inside of the sine function. Now when we're thinking about a composite function like this, we have to think about what we're putting inside. So here we've got our x squared is our inside function. So when I'm substituting values in first, what I do first is that I substitute x values into the x squared part of the function. So if I have f of g of x as my composite function, what we do is that we start with g of x and I start by putting into my inside function all of the different x values. And if I want to know which x values are possible, that means that what I'm doing is that I'm substituting in the domain of g. So I can only substitute in possible values that x can take. In our case up here of x squared, our domain of x squared is the reals, so I could put all of the reals into my inside function. Then we have something coming out. So after I've substituted in my x values, if I sub x values into a function, what I get out of that is the possible y values. So when I substitute into x squared, for example, that x equals 2, what I would get out is the y value of 4. So the possible values that can come out of my inside function is the range of that, because the range tells us the possible y values that I can come out, so the possible outputs. The inputs to my inside function is the domain, and the outputs of my inside function is the range. Then what I do, so once, if for example up here again, if I'd have substituted in x is 4 into my inside function, what comes out is that, because we know y equals x squared, if this is my inside function, what would come out would be 16. Then I would need to put this value of 16 into the next function, the outside function. So I then get to my f of x function and I'm trying to put into my f of x function, I'm trying to take the range of g here and put it inside there into my f of x. But I'm only allowed to put certain values into my outside function. Once again, what I'm substituting in are the x values of this f of x function. So what I'm trying to put in there is the domain, the possible x values that this function can take. In my example up here, if I'm trying to substitute 16 in here, if I'm trying to work out sine of 16, that is going to be possible because we know that the domain of sine is the reals. So we put in our domain of f, and what comes out of that is that we're wanting our y values again once I substitute in x values. So once I substitute in sine of 16 out of here, I will get a particular y value, which is otherwise known as our range of f. Now the problems that come in along the way, and this is what we'll be talking about, is if this range of g does not match exactly this domain of f, and that's where this gets a little bit tricky. So we've got a few little points up here. It tells us if f of g of x exists, range of g is a subset of domain of f. So that means this range of g must be smaller or equal to the domain of f. The values that I get out here, they have to fit within our domain, otherwise I can't put them into my next f of x function. So this is what we need to do if we want to prove that a composite function exists. We're looking to prove that this range of g is in fact a subset of the domain of f, that it can fit inside. When that happens, if that's true, then the domain of f of g of x is equal to the domain of g. So if, and this is going a little bit further, if these two things here are actually equal, then the domain of my composite function is this part at the start, and the range of my composite function is this bit at the end. If they are not equal, then this is where both the domain and range of the composite function will need to change, and that's what we're going to be getting onto in these next few examples. So let's start having a look at some particular examples. So here we've been given two functions. We want to determine the rule g of f of x and f of g of x. What we do first is that we do a brief sketch of the two functions. So if I'm sketching the x squared function, g of x, it's just going to look like this. Excuse my slightly bad drawing there. Y equals x squared. And we will have the domain is going to be the reals, and the range is going to be from 0 to infinity. Or we could say that as the positive reals including 0. The f of x function, it's a log function. This minus 2 means it's been translated to the right by 2. So this particular function here that I'm looking at, if I do a quick sketch, it's been translated to the right by 2, which means our asymptote has moved to the right by 2. So it's going to be looking like this. So again, we can get the domain of this function, which does not include 2, and the range of this function, which is the reals. So now we're ready to start our flowchart to see along the way what happens in each case. If I'm wanting to find the composite function g of f of x, that's the same as saying g of f of x like this. So f of x is my inside function. The composite function I'm finding, g of x is my outside function, something squared. The inside function is this bit here. Now we want to see if this exists, what the domain and range will be, or actually state the maximal domain for each function to exist. So we start with our inside function, which is f of x in this case, and then we're going to get on to g of x, our outside function. So first we want to know, what do we put into f of x? So if we start with our f of x function, let me label them here so I don't forget. This is g and this one here is f. So what goes into our f of x function is this domain. So the domain of f is what goes in. That's the allowable values. I can put in any number from 2 to infinity into this function, and it will give me an answer. It will give me a y value. If I was to put in any number from 2 to infinity into my log e of x minus 2 function, I would get out of that the range of f. So what I would get out is all possible real numbers, all possible reals. Then the domain of g, what I'm wanting to do now is to put values into my outside function. So once I get a y value out from this log e of x minus 2, I'm then going to square it because my outside function is this x squared. Now, the domain of g is the reals. And if that all works, what I'd be coming out of here is the range of g, which is the 0 to infinity. We worked that out before. So if we think about what's going on here, because this range of f is exactly equal to this domain of g, we don't need to do anything to change our initial input or our final output. Because what this is saying is I can put in any numbers from 2 to infinity into my f of x function and I will get out all possible values, all possible real numbers. And it is also possible for me to substitute all possible real numbers into the x squared function, which does make sense. No matter what number I get, I can successfully put it in here for x, square it, and I'll get another number. But my range that comes out will only be from 0 to infinity. Because these two in the middle here are the same, we do not need to do anything more. Okay, so that's important. If these two inside things are the same, then we're just straight away done. And our part at the start here, this is the domain of the composite function. So the domain of g of f is equal to 2 to infinity, not including the 2. And the range of g of f is the part that came out over here, which is from 0 to infinity. Okay, so when the two in the middle are the same, it's quite easy. We don't have any problems, so we can move happily along. Now let's go on to our second case, if I'm wanting to find f of g of x. So this time f of g means that I'm finding, the other way of writing that is f of g of x like so. What I'm doing is I'm starting with my f of x function, and instead of x, I'm replacing the x by the inside function, which is x squared. Okay. So this time we start with g of x, we start with the inside function, and then we go to the outside function. So just to keep that in mind, we start with our inside function. We have our arrows, our domain going in and our domain coming out, and then we get to our outside function. And we have the domain going in and the range coming out. So back to this specific one here. What possible values of x can we substitute in here into g of x? So our allowable possibilities is the domain of g, and the domain of g is the reals. The possible things that could come out would be our range of g, and our range of g is 0 to infinity. Possibilities to go in to f of x, domain of f, which is 2 to infinity, and what might come out is the range of f, which is the reals. Now this is where we run into a problem, because if we have a look, this time the range of g is not the same as the domain of f, okay? When these two are not the same, that means that I'm going to have to alter either the maximal domain for the function to exist, or the final range will be different. Because looking at this function does not currently exist. Remember that for a function to exist, what we would need to happen is that we would need the range of g to be a subset of the domain of f. And it's not at the moment. The range of g is bigger than the domain of f. So at the moment, it's not true. It does not exist. So how we're going to make it exist means that we're going to need to restrict this domain. I'm only allowed to put in values from 2 to infinity into f of x. That means I need to change this range, so it's only going to go from 2 to infinity, because that's the only allowable values that I can actually substitute in. Now if I'm only allowed to put values from 2 to infinity, if the range of g has to be from 2 to infinity, that means that the domain of g is going to change. If I'm only allowed to have from 2 to infinity from g, that means I'm only allowed to have from this point here up there, and from this point here upwards there. Not this bit here, because that would be giving me values between 0 to 2, which we cannot substitute in. If I tried to substitute a value of 0 in here, x equals 0, into my f of x function, I would get log e of negative 2, which is not possible. We can't have logs of negative numbers. So I have to change my range. Now if I'm wanting my range from being to 2 to infinity, I've got to figure out what the corresponding domain is, which means I have to figure out what these x values will be. So I let my equation x squared equal 2. I'm letting it equal the y value. If I solve this, I take the square root, so I get positive or negative square root of 2. So that means that my new domain, I'm allowed to have values from negative square root of 2 to infinity, and in union with square root of 2 to infinity. So it's changed the maximal domain for this function to exist. Because we changed, so going back again, we needed these two inside values, subsets, to be the same. Because we changed the range of g, we had to change the domain of g, which means that we've got a new maximal domain for this function to exist. Because I did not change the domain of f, it has not changed the range of f, so the reals is still the range of this composite function. So finally we can say that in this case here, the domain of f of g is equal to our domain that we had there. This is the maximal domain that will allow this function to exist. And the range of this composite function is the part that we got out at the end, which is all possible real numbers. So using these flowcharts, yes, it can be time consuming, but I highly recommend it. It's a very good method to make sure that you can absolutely 100% identify your maximal domain and the range of a composite function. Let's have a look and try another example. Okay, so let's have a look at our past exam question that we've got here. So f of x is defined. Notice that we've got the domain of f of x given here, and g of x, we've got our function here. To start with, to find the rule, remember that for a rule, we just need an equation. Remembering that if you were asked to find the function, then in that case, you would have needed to do the whole thing with our domain to reals and written the whole thing. So just keeping that in mind. But in this case, we just want the rule. So our rule is going to be h of x is equal to our f function is the outside function. So I start writing my outside function. But instead of x, I'm going to replace it with g of x. So I put g of x here where the x normally goes. Note also that when writing with logs, we need to make sure that the e here is a subscript. It's little. It's not the same size as the g. So that's it. That's all we needed to do for the first one. The second one, however, stating the domain and range of h, this is going to be a little bit trickier. And this is where using the method from the previous part where we were talking about our flowchart is really helpful. So if we start with our function f, if we want to get the domain and range of that, let's do a really quick sketch. F, it has a asymptote here at x equals 0, and log e looks like something like this. So the domain is from 0 to infinity, and the range is the reals. If we look at our g of x function, it's a parabola that has been moved up 1. So the domain of our g function is the reals, and the range is from 1 to infinity, including 1. So this is where good function knowledge is really important for everything that we do. Now we're wanting to find the domain and range of h. G of x is the inside function, so that's where we start. We're going to have g of x, and then we're going to consider f of x. So what goes into g of x is our domain of g, which is the reals. What comes out of g of x is the range of g, which in this case is from 1 to infinity. What goes into f is the domain of f, which is from 0, round bracket, 0 to infinity. And what comes out of f is the range of f, which is the reals. Now remember what I said earlier, we want these two subsets here to be equal. Because they are not, that is going to change something. Now does this function exist? Is the range of g of x a subset of the domain of f? Yes, it is. So if I wanted to ask if this function exists, yes, it does exist, because the range of G is a subset of the domain of F, which means it is either the same size or smaller, and it's actually smaller. So we know it exists, which means we do not have to change this range, which means we do not have to change this domain. However, because these are not the same, it is going to affect our final range. So if I'm only allowed to put values from 1 to infinity into f of x, I can't possibly put 0 in, because there is no way that 0 is coming out of g of x. No matter what x value I put into this y equals x squared function, I am never going to get an answer of y equals 0. So I can never put this 0 in, or 1, or sorry, I can put in 1, but I can't get 0.5. So what we need to do is to change that. So while f of x is allowed to have values from 0 to infinity, the only numbers available to me are the numbers from 1 to infinity, because those are the only numbers we have coming out of here. These are the only numbers I had coming out of g of x, so I can only put 1 to infinity into my f of x function. If I only put values from 1 to infinity in here, I need to find what happens when x is 1. So if I substitute x is 1 into this f function, I'll get log e of 1, which is 0. So I get this point here is the point 0, 1. Other way around, sorry, 1, 0. So that means that the range of this, if I'm only allowed to put in values of x from 1 to infinity, I'm only going to get these values here, but I do include that point because I can get a value of 1 from previously. That means that the new range that I'm going to get is going to be from 0 to infinity. The possible y values of this green part here are from 0 to infinity. So now, once we've made sure that our two parts in the middle are the same, the domain of h is the part I had at the start, which is the reals, and the range of h is the part I had coming out at the end, which is 0 to infinity. Okay, let's do another example. So this one's a little bit different, but let's have a look through it together. It's phrased in a slightly different way, but we're still looking at the same things, the same general idea. To start with, we want to state the range of f. Always a good idea to sketch if we're not sure what's going on. And again, notice we've got a restricted domain here. This +1 that we've got here means it's been translated to the left by 1. So my square root function, my f function, is translated to the left by 1. This is what it would normally look like. But I only want to go from 0 to infinity, which means I actually only want to go from here which means that we actually don't need this bit. Oh, I've rubbed out the whole thing. So what we actually want when I'm going from 0 to infinity is that I'm just going to have this bit. And if I substitute in when x is 0, I would get the square root of 0 plus 1, which is 1. So we start here at the point 0, 1. This means that the range of f, according to that restricted domain, is going to be from 1 to infinity. Notice that I have a square bracket because we had a square bracket here. The point where x is 0 is included. Alright, moving on. Part B. Now we've got a second function here that says g of x equals x squared plus 4x plus 3, so that's a parabola. We've got a domain here, a restricted domain, but we don't know what c is yet. And we're wanting to find the largest possible value of c such that the range of g is a subset of the domain of f. Now, the domain of f we know because we had that before. It's 0 to infinity. Domain of f, it's up here, 0 to infinity. So we need to figure out what the range of g is going to be so that it will fit within 0 to infinity. That means we need to sketch g of x. So when we're sketching a parabola, useful things to know are intercepts and turning points. If we're trying to find the intercepts, we need to factorize this. So factorizing, we would get x plus 3 and x plus 1. So that means the x-intercepts will occur where x equals negative 3 and x equals negative 1. So if I'm doing a quick sketch of this, when x is negative 3 and negative 1, I'm going to be getting a parabola looking, it's a little bit uneven, but negative 3 and negative 1. Now the turning point is going to be halfway between them, so it's happening at negative 2. And if I wanted to substitute in negative 2 into my g of x function, I would get negative 2 squared is 4. 4 times negative 2 is negative 8 plus 3. So negative 4 plus 3 is negative 1. I've got a turning point here of negative 1 to infinity. Now, the range of this currently, from what I'm looking at, if I do nothing to change it, the range of this function is going to be from negative 1 to infinity. But that is not a subset of 0 to infinity. So if I want this to be a subset of 0 to infinity, that means I can't have anything underneath the x-axis. So I want this range to be just from here, including 0 upwards, or from here upwards. So for this range of g to be a subset of the domain of f, the domain of f that I'm looking at here, the domain of g that I'm looking at here could be from negative infinity to negative 3 and from negative 1 to infinity. But we were told that the domain of g has to be just from negative infinity to c. If I'm just going from negative infinity to c, the only part I want is this part here. So I'm just going to go from negative infinity to negative 3. So c is equal to negative 3. So that's what we're looking at there. Now we can't have, if I had suggested c was negative 1, that would mean that I'd be saying that we're wanting to go from negative infinity to negative 1, from negative infinity to negative 1. That would give me a range which includes negative numbers. So that would not, therefore, be a subset of our 0 to infinity that we're looking for. What we want to do now is to state the range of this. So if we're looking at our patterns like we've done before, so remember we're looking at f of g of x. G of x is the inside, so we have g of x first, then we have f of x. So we put into g of x the domain of g, which we just worked out previously, is negative infinity to negative 3. The range of g, now that we've restricted it, because that's what we were doing by choosing the domain of negative infinity to negative 3, the range of g, now that we've restricted it, is going to be from 0 to infinity. The domain of f always was 0 to infinity, and the range of f was 1 to infinity. So, because these two middle values are the same, we made them the same with part 1. That means that the range of f of g of x is this range here that's coming at the end of our flowchart. So our final answer, and we need to make it clear what our final answer is when we're doing exams, is that the range is equal to 1 to infinity, with the 1 being included. Part C, we're now wanting f of h. So we know everything about f, but h is different. So we'd better find out some things about h. So let's draw a quick sketch of h. It's a parabola again, but this one's been translated up 3, so it's a parabola here with the point being 0, 3. So our domain is the reals and our range is from 3 to infinity. So we start with our inside, which is h of x. Then we're going to get to our outside, which is f of x. What goes into h? The possibilities going into h, which we just found out our h over here. Our domain of h is the reals. What comes out of h is the range of h, which is 3 to infinity. What we're wanting to put into f, now our domain of f that we had defined right up here at the start was 0 to infinity, and the range of f we had at the start was 1 to infinity that we established in part A of the question. Now, hopefully we recognise we've got a problem. These two values in the middle are not the same. So we have to make one of them smaller. 3 to infinity already is small, so we're going to make this one here smaller. We need to make that 3 to infinity as well. If I can only put x values of 3 to infinity into f of x, that means that I'm going to have to start off my f function here at 3, and I'm only allowed those y values then. If I substitute x equals 3 into my f of x function, I'm going to get square root of 3 plus 1, which is the square root of 4, which equals 2. So the domain of this, if I have to start this at 3, my smallest y value is 2, so it means that my range is now going to be from 2 to infinity. So therefore the range in this case is going to be 2 to infinity. Remember, to know the domain and range of the composite functions, we need the two inside parts of our flowchart to be equal. All right, one last example. Now this one is multiple choice, which means that it was on the exam 2, which means you do have a calculator. But you actually can't use a calculator for this anyway. This is about an understanding of composite functions. We're wanting to find out what f of g of 3 is. So we start by finding out what g of 3 is. We start with the inside function. G of 3, we're told up here, is equal to 2. So I'm going to replace that g of 3 with a 2. I haven't done anything with my outside function f yet. Now I need to find f of 2. Well, f of 2 over here is 5, so f of 2 is equal to 5. And that means that our answer for f of g of 3 is 5. So that's all we've got for today about composite functions. I hope that makes a bit more sense to you. Feel free to come and see me if you have any questions along the way. Thanks for watching.